Alright, so one more video in Chapter 8, and like I mentioned at the end of the last one, we're going to see a really cool reaction now. This reaction is called the Diels-Alder reaction. Alright, so it's was developed by two German chemists so let's take a look at what we get out of this reaction. Alright, so this reaction is going to combine two pieces that we've learned about before. Alright, we're going to start out with the diene. Alright, we've been talking about diene reactions. And the other one is just an alkene, but it reacts with the diene. It loves dienes, so we call this a dienophile. Alright, a diene lover. Alright, so watch this. We're just going to mix these two compounds together, and we're going to heat it. That's all we do. And we're going to get this product over here. Look at that. So how do we get there? Right? Notice that important things here, we've actually formed two carbon-carbon bonds at the same time. Alright? And our product is this cyclohexene. Alright, so let's see if we can figure out what's going on here. Alright, so I'm going to redraw this a little bit. I'm going to take this diene. Remember, there's two different conformations of a diene like this. This is called the S-trans. But if we rotate around here, it's kind of a hindered rotation, but we can get another conformation that looks like this. This is the S-cis. Okay, so the S-cis is required for the Diels-Alder reaction. Alright, so if there's a molecule where there's more rings or something and it can't rotate into this S-cis conformation, then the reaction won't take place. Alright, so then we have our dienophile like this. Alright, so the way that this works is that one of the double bonds, we think it like this, it's an electrophilic reaction. The pi bond of the diene attacks the dienophile, makes a bond right there. This bond goes over to there, and this bond goes like this. So what does this remind you of, right? It's the same kind of arrow pushing that we see in benzene. Right, so let's draw out what we get. Right, so let's just draw the two carbon skeletons first. Alright, so we have formed, I'm going to draw the new bonds in blue. Alright, so we formed a new bond right here. Right? We formed a double bond over here that wasn't there before, and we formed a new bond right here. Alright, so we actually formed two new sigma bonds and one new pi bond. Alright, so this is the Diels-Alder reaction. This reaction tends to work the best if the R group is an electron withdrawing group. Okay, and they tend to look like this. So R can equal things like this with, here's the bond, with carbonyls with various things over here. A nitrile works. A nitro group is an electron withdrawing group, and what happens in these cases is that we have our dienophile with, say, our electron withdrawing group here, and so essentially we have a diene here that would have resonance that goes, like we looked at before, in this direction. right? So we have a resonance contributor that looks like this with a plus, and this plus makes it a stronger electrophile, right? So if we have say a delta minus on this side, it reacts with the delta plus of the dienophile. So let's look at examples. All right, so here's various examples here. Okay, so here we have the diene, and this one is the dienophile. Okay, so remember we have, here's the alkene of the dienophile, and this part is the electron withdrawing group. Okay, so let's line these up so we can do the reaction. All right, so we're going to rotate this one, and we're going to draw it like this. Notice that it has these two methyl groups attached, so those methyl groups are now here. Then we have the dienophile, and we have this electron withdrawing group. Okay, this electron withdrawing group in this case is called an ester. Okay, now we can draw the arrows around. So remember that this is the delta plus end, so our arrows would go this way, and like this. And this is going to give us a cyclohexene, right? We're going to have the extra double bond over here. We have two methyl groups there, and we have our ester over here. All right, so let's try the next one. Look at this one; it's kind of fancy. Okay, so we have a cyclic diene, and it's going to react with our dienophile, which is just ethene now. But so the same reaction is going to take place. This is going to go over here, this is going to go here, and this is going to go here. So what we're going to get, we can draw it in two different ways. We're going to get this, and we're going to have this group bridging across. Okay, this is called a bicyclic ring system. Okay, we have two rings together. All right, another way to draw this, which is kind of hard to do it if you haven't practiced, is to have it like this. And our double bond is over here. So what we notice in this case, so here's the cyclohexene down here, but this extra carbon that's over the top is bridging up and over the top. Okay, so this is the bicyclic product. All right, we can have various bicyclic ones. So we could have various things with like an oxygen up here. We'd have an oxygen over here. We could have two more carbons on there. I'll show you a couple more examples in just a second. All right, so let's look at this last one. Look at this. Here's the diene. It's just 1,3-butadiene, but look at our dienophile. That thing is nasty. It has a triple bond in it now. OL-C8-5, so it has electron withdrawing groups. But the alkyne is going to react just like the alkene, right? So this can go here. One of these pi bonds is going to go here and around in a circle. So let's see, we're still going to get a ring like this. We still have this double bond here, but because there was two pi bonds here, one is going to be left over still. So we have another pi bond here, and then we have our two esters. Like that. So now we have a cyclohexadiene. All right, let's look at just a few more fun examples. Alright, so I'll show you a couple more bicyclic ones. So let's say we start with this diene, okay, and let's just, what should we do? We won't make this too complicated. Let's just use ethene again. Alright, so this goes here, and this goes back down there. So in this case, alright, we heat this. We just have 2 carbons over the top. Like that. Alright? So those are kind of fun to make. So let me show you one more example. Alright, so we're going to start with this, and I'm going to add a OL-C8-5 on here. Okay? And that's going to react with, let's just make this, I'm going to make this a nitrile here. Alright, so we have 2 different possibilities here. Right? And it depends upon how the diene and the dienophyte line up with one another. Okay, if they line up this way, oops, OCH3, and this way, then what would it give us, right? This would go like this, this, this. This would give us our OCH3 here, double bond there, and our nitrile over here. Okay, so the other possibility is that the diene is the same, but we flip the dienophile over. So in this case, the nitrile is pointing down. Alright, we're going to have the same type of reaction. And what do we get? We get OCH3 here, double bond there, but our nitrile is down here. Okay? So what's the relationship between these 2 products? Right? So these 2 products are constitutional isomers, right? What do you think? Is one going to form more than the other? Well, of course it is, right? So what we have to consider here is the polarity of the diene and the polarity of the dienophile. Alright, we already talked about that if we have electron withdrawing groups, they're going to pull electron density back this way, and what we're going to end up with is a plus on the end. Alright, so if we line these up, we're going to have a delta plus on this far end. Okay, so let's look at the diene now. So what is this methoxy group going to do to the polarity of the diene? Alright, so on one hand we think, oh, this is more electronegative, it's going to pull electron density away from it. But the thing, if we jump to that we forget is that oxygen has non-bonding electrons on it. And so what oxygen tends to do in this arrangement is donate electrons like this. And if we do that, then we come up with a resonance contributor like this. Okay, so that tells us that even though we had a delta plus over here, we have a delta minus on this end of the diene. So the way we predict the product is we line up the delta plus end of the diene with the delta the delta plus end of the diene, the delta minus end of the diene, and the delta plus end of the dienophile. So if we have the plus end down here, we want to put the minus end of the diene over here. So that means the OCH3 is going to go down here, and this is delta minus. Okay, so we're going to pair these up. And the only way we can pair them up is to know how this resonance works. Okay, so this is the minus end, so that minus end goes to the plus end, and then we just draw the rest of our electrons around in a circle, make our cyclohexene, and this is our product. Okay, so it was this one over here. Alright, so that's all we're going to learn about the Diels-Alder reaction. Okay, so in this chapter we first learned about resonance. We learned how to use arrows to draw resonance contributors, and we learned a series of rules to be able to predict which resonance contributors are more stable than others. And remember that the true structure is a hybrid, a weighted hybrid of all of the resonance contributors, with the more stable ones weighted or contributing more. All right. We then went on to learn about a certain type of resonance, and these are in the aromatic compounds, so benzene type of compounds, and we learned about what it takes to be aromatic, and we looked at some other types of aromatic compounds. We then went into two different videos talking about how resonance can affect reactivity. The first type of reactivity was acid-base chemistry, so we were using resonance to influence the stability of either conjugate bases or conjugate acids. And then we looked at the addition to conjugated olefins, and we saw that we could get two different kinds: thermodynamic control, or that's kinetic control, and thermodynamic control. In this final one, we learned about the Diels-Alder reaction. We're able to make really pretty complicated molecules in a simple single reaction. All right, there we go.